Welcome back to the deep dive. So in the AI world, things move incredibly fast, right? And just calling a general model API, well, that's not really the cutting edge anymore. The real advantage, the next level performance that comes from building specialized AI experts. And the main way to do that, the key technique for turning those brilliant generalists into domain-specific masters, that's fine-tuning.
Exactly. And our mission today is really to give you that end-to-end roadmap. How do you actually build your own custom generative models? We'll kick off with the strategic why, like why even bother. Then we'll dive into the cool techniques, state-of-the-art stuff like PFT. We'll also look at, the deployment side, which is crucial but often overlooked. And finally, the operational stuff, LLMOps, monitoring, security, automation, all that good stuff.
Right. So by the end of this deep dive, the goal is you won't just have like code snippets. You'll have the strategic thinking and a technical know-how to actually build these next-gen intelligent applications. Okay, let's unpack this. So when we first started with LLMs, prompt engineering was kind of the main way in, wasn't it? Like giving really detailed instructions. But fine-tuning feels, I don't know, deeper. How does it actually change what the model can do? And prompting just can't.
That's a great question because it is fundamentally different. Prompting is instructions, like you said. Fine-tuning, though, it actually teaches the model a new skill. It changes its internal parameters, the weights. Think of it like this. Prompting is giving someone directions for one specific trip. Fine-tuning is sending them to driving school so they can navigate anywhere. It's a lasting change.
Okay, that driving school analogy really works. It's about embedding the skill. So given that deeper change, what are the really big wins for production AI apps? Why is it essential?
Well, first and foremost, performance and accuracy, especially for niche tasks. General models just don't have the specific jargon or context. Fine-tuning boosts that accuracy and relevance dramatically. Imagine like a generic chatbot trying to handle support tickets for specialized software. It'll probably mess up the terms. But you fine-tune it on past tickets. It learns the lingo. High precision.
Yeah, I can see that. Accuracy is huge.
Yeah.
But you also mentioned cost and latency. It feels really important at scale. How big a deal is that in production?
Oh, it's critical. Absolutely critical. Think millions of requests. Inference costs add up fast. Generic models often need really long, detailed prompts, maybe with examples, to work well. That's more tokens, more cost per call. A fine-tuned model, it already knows the task. Shorter prompts, that directly cuts API costs and speeds things up. Huge economic driver at scale.
And it also gives you more control over how the model behaves, right? Like tone of voice, output format.
Exactly. Deep behavioral customization. You can fine-tune it to match your brand voice perfectly or guarantee it outputs clean JSON every time or even, make it write like Shakespeare if you really wanted to. It gives you that fine-grained control. And another big one, often overlooked, is data privacy. You can train on your sensitive data, maybe customer examples, without ever exposing that data during actual use, during inference. The knowledge gets kind of baked into the model's weights in your secure environment. No risk of leaking PII and prompts or responses later.
Okay, so baking the knowledge in. When we talk about updating those weights, how do we actually do it? Are there different methods?
Yep. Two main paths, fundamentally different. First is full fine-tuning. Simple idea, update all the weights. But for today's huge models, billions in parameters, it's incredibly resource hungry, needs massive compute, often just impractical unless you're, Google or OpenAI. It's like trying to repaint a whole battleship just to change one panel.
Right, okay. Impractical for most.
Exactly. Which leads us to PEF, parameter efficient fine-tuning. This was a total game changer, a real paradigm shift. Made fine-tuning accessible, the core idea, freeze most of the big pre-trained model, keep all that general knowledge locked in, then only train a tiny fraction of new or existing parameters. This slashes compute and storage needs, sometimes by like 10,000x. And a key side benefit, it helps avoid catastrophic forgetting.
Catastrophic forgetting.
Yeah, where the model forgets its general smarts while learning the new specific task. PEFT mostly avoids that by leaving the original brain intact.
Okay, 10,000x cheaper, and it doesn't forget. That sounds like the way to go. So within PEFT, are there different flavors, different ways to do this efficient tuning?
Definitely. There's a whole spectrum depending on your goal. The most common is SFT-supervised fine-tuning. This is your basic labeled data approach. You feed it prompt response examples, teach it a specific skill, style, format. Great for classification, maybe nuanced translation.
Okay, standard supervised learning. What else?
Then there's RLHF reinforcement, learning from human feedback. More complex, multi-stage. Used to align models with human values, like being helpful and harmless. It usually starts with SFT. Then you train a separate reward model based on humans ranking different responses. Then you use RL to tune the main model to get high scores from that reward model. Crucial for safe
Right,
chatbots.
the alignment step. Complex, but important.
Very. And newer methods are emerging to make that easier, like DPO direct preference optimization. It skips the separate reward model, optimizes directly on preference pairs which response did a human prefer. More efficient for things like improving summaries or tweaking tone.
Interesting. So alternatives to RLHF.
Yeah. And for really reasoning-heavy tasks, there's RFT reinforcement fine-tuning. Think medical diagnosis or legal analysis. Here, experts grade not just the answer, but the model's thinking process, its chain of thought. You reinforce the good reasoning paths. Really powerful for complex domains.
Wow, okay, so a whole toolkit, depending on the problem. Now, something that often comes up, fine-tuning versus RAG, retrieval augmented generation. People seem to mix them up. What's the difference? When do you use which?
Ah, yes. Crucial distinction. They serve very different purposes, though they can work together. A RAG is like giving the model an open book at inference time. You retrieve relevant documents or facts and stick them in the prompt. It's great for adding knowledge that changes often, like today's news or your latest product specs. Enhances factuality, reduces making stuff up. You just update the book.
So a RAG is about external knowledge, real-time facts.
Exactly. Fine-tuning, on the other hand, changes the model's internal knowledge and skills. It retrains the brain itself. Best for stable knowledge, like understanding medical terms, or inherent skills, like writing in a specific brand voice or coding style. Things that don't change day to day.
Okay, so RAG for facts, fine-tuning for skills or style.
Pretty much. But they work great together. You can fine-tune a model to be better at using the information provided by RAG. Makes the answers more accurate, better formatted. Synergy. And this ties back to strategy, right? General models are becoming commodities. Fine-tuning lets you leverage your unique proprietary data to build a unique, defensible AI asset. It's about moving from just using AI to actually building unique AI.
That's a powerful point, building defensible assets. Okay, you said PEFT was the paradigm shift, and LoRa is a key technique there. Can you unpack LoRa a bit? What's the magic behind its efficiency?
Absolutely. LoRa, or low-rank adaptation, is based on a really clever observation. It turns out that when you fine-tune a huge model, the change in the weights across all those billions of parameters can often be represented or approximated really well by two much smaller matrices. Think of it like, instead of adjusting every single tiny knob on a giant control panel, you find two master knobs that achieve almost the same result. These small matrices have a low rank, mathematically speaking.
Okay, so you're approximating the big change with a small change.
Precisely. So, in practice, you freeze the original huge model. Then you inject these small trainable adapter matrices, usually called A and B, into certain layers, often the attention layers. And you only train these tiny A and B matrices, nothing else.
And it has big benefits.
Massive benefits. First, parameter reduction. You might be training 10,000 times fewer parameters. That drastically cuts the VRAM needed.
Okay, less memory. What else?
Second, crucially, no inference latency. After training, you can actually mathematically merge the learned adapter weights, A times B, back into the original frozen weights. So when you deploy the model, it has the exact same architecture as the original. No extra layers, no slowdown. It's just been updated.
That's clever. Merge them back in.
Yeah. And third, these adapters are tiny, maybe a few megabytes. So you can train lots of different adapters for different tasks, summarization, classification, etc., and store them easily. Then you can load the base model and quickly swap in whichever adapter you need for the current task. Very efficient multitask deployment.
Incredible. Less memory, no latency hit, swappable skills. But can you push it even further? I've heard of QLoRA. How does that improve on LoRa?
Ah, QLoRA. Yes, QLoRA takes LoRa's efficiency and cranks it up another notch, mainly by tackling the memory footprint of the base model itself. Its big trick is quantization. It takes the huge frozen base model weights, which are usually stored in 16-bit precision, and compresses them down to just 4 bits.
4 bits. Doesn't that lose a lot of information?
You'd think so, but QLoRA uses a very clever 4-bit format called NF4, normal float 4-bit. It's information theoretically optimal, apparently, for normally distributed weights like those found in neural nets. It keeps more precision around the values that matter most. And it only dequantizes tiny chunks back to 16-bit right when they're needed for computation, keeping the overall memory usage super low.
Wow. So compress the base model to 4-bit.
Exactly. And it has other tricks too, like double quantization, compressing the quantization constants themselves, and paged optimizers to cleverly swap memory between GPU and CPU if you hit memory spikes during training.
Okay, these sound like serious optimizations. What's the end result? What does this enable?
The result is pretty staggering. QLoRA can slash the memory needed to fine-tune, say, a 65 billion parameter model from over 780 gigabytes down to less than 48
Wait,
gigabytes.
780 gigabit down to under 48 gigabit.
Yeah, which means you can fine-tune that massive 65B model on a single high-end GPU, like an A100 or H100 with 48 GB or 80 gigabit of VRAM. And critically, it does this while maintaining the performance level of a full 16-bit fine-tune.
That's truly game-changing. It basically puts fine-tuning these enormous models within reach of researchers, startups, smaller teams, not just the giants. It's a democratizing force, isn't it?
Absolutely. That's the perfect word for it. QLoRA was revolutionary because it showed how clever software and algorithmic tricks could make existing, accessible hardware vastly more powerful. It proved that staying cutting edge isn't just about having the biggest hardware budget. Mastering these software techniques is just as crucial, if not more so.
Okay, so quick summary then. LoRa versus QLoRa. How do you choose?
Right. Basically, LoRa keeps the base model in its original precision, like 16-bit. QLoRA quantizes it down to 4-bit. Memory-wise, LoRa needs moderate GPU memory, maybe 1624 GB for a 7B model. QLoRA needs very low memory, enabling those huge 65B models on a 48 GB GPU. So the rule of thumb, if your base model fits comfortably in your GPU's VRAM, LoRa is great for efficient training. If the base model is too big for your VRAM, QLoRA might be your only option to fine-tune it at all.
Excellent clarification.
Oh.
Okay, we know the why and the how. Let's talk tools. The Hugging Face ecosystem seems unavoidable here. Why is it so central? Like the GitHub for AI.
Yeah, that's a good analogy. The Hugging Face Hub is absolutely the central hub.
Yeah.
Millions of models, data sets, demos, it's the starting point. Key skills you need. Finding models effectively using search and tags, understanding the model cards, those README files explaining what the model is, how it was trained, its limitations, biases, and knowing how to access it programmatically, like using the Hugging Face Hub login function in your code to download models or upload your fine-tuned versions.
And beyond the hub itself, there are the libraries, right?
Exactly. The libraries are the workhorses. Transformers is the big one, provides all the models, auto tokenizer. And the trainer API we'll get to. Datasets is for loading and processing data super efficiently, load dataset, the map function. Evaluate makes calculating metrics easy. Evaluate.load accuracy. PEFT contains LoRa, QLoRA, and other parameter-efficient methods, LoRa config. Accelerate is kind of the magic glue for training, makes your code run on CPU, single GPU, multiple GPUs, even TPUs, with minimal code changes. And Bitsandbytes is the specialized library that provides the low-level stuff for QLoRa's 4-bit operations. They all work together pretty seamlessly.
Okay, you mentioned the trainer API. Writing training loops manually can be painful. How much does trainer really simplify things?
Oh, immensely. It abstracts away tons of boilerplate. Setting up optimizers, schedulers, gradient accumulation, mixed precision, distributing across GPUs, logging, saving checkpoints, evaluation loops. Trainer handles all that. The basic workflow is you set up training arguments that's like a big config file controlling everything from learning rate to save frequency. You define a compute metrics function for evaluation. Then you instantiate the trainer with your model, args, datasets, tokenizer, and that metrics function.
And then just .trainer.train.
Pretty much. That one line kicks off the whole optimized, distributed, aware train-in process. Its real power is abstracting the hardware complexity. Write it once, run it on your laptop, then just change the config to scale it up to a multi-GPU server. Huge productivity boost.
Any advanced tricks?
Yeah, it's extensible. You can subclass it for custom behavior or use callbacks for things like early stopping, logging to experiment tracking tools, etc. And this whole ecosystem feeds itself, you know? Researchers share models on the hub. Developers use transformers, PEFT, trainer to fine-tune them. Then they often share their improved models back using trainer.push-to-hub. It's a virtuous cycle accelerating the whole field.
Fantastic. Okay, theory and tools covered. Let's make it concrete. Project 1, fine-tuning for specialized classification. Let's say building a financial sentiment analyzer.
Great example. Very practical. Goal: classify financial news headlines positive, negative, neutral. And it's a good challenge because generic models get confused by finance speak, like hawkish Fed stance, is that good or bad? A fine-tuned model learns those domain nuances. We could use, say, Distilbert base uncased and efficient BERT variant and the financial phrase bank dataset from the hub. Its sentence is already labeled by finance experts.
Okay, walk us through the key steps.
Right. Step 1, setup. Install libraries, log into the hub, huggingfacehub.login. Step 2, load data. Low data set, financial phrase bank, sentence allegory, split into train test. Remember the labels are numbers, 0 negative, 1 neutral, 2 positive. Step 3, load tokenizer and model. auto tokenizer, and auto model for sequence classification. Crucially, tell the model num labels 3. Create id2 label and label 2 id maps so you get readable outputs like positive, not just 2. You'll likely see a warning about unused weights. That's normal. It means it dropped the pre-trained model's old head and added a new one for your classification task.
Okay, got it. New head for the new task.
Step 4, pre-processing. Write a function to tokenize the sentences, truncation true. Apply it using dataset.map, batch true, for speed. And a key best practice here. Use data collator with batting. It does dynamic padding, pads each batch only to the longest sentence in that batch, not the absolute longest in the dataset. Saves compute, speeds things up.
Smart. Dynamic padding.
Step 5, evaluation setup. Define your compute metrics function. Use evaluate.load accuracy, and maybe evaluate.load F1. F1 is often done for classification, especially if classes are in balance.
Good tip. F1 over just accuracy.
Step 6, train. Configure training arguments, output directory, learning rate, batch size, epochs, set evaluation strategy epochs, save strategy epoch, load best model attended true is good practice, push to hub. True, instantiate trainer with all the pieces, then just call trainer.train. Step 7, evaluate and deploy. After training, run trainer.evaluate on the test set. Then trainer.pushToHub uploads the model, tokenizer config, results, everything needed to reuse it.
Excellent. That seems very manageable with the trainer. Okay, project 2, generative tasks, summarization. You mentioned the architecture shift is key here. Moving from Distilbert encoder only to something like T5 encoder-decoder, how does that change things?
It changes quite a bit under the hood. The core principle, prepare data, configure training, run trainer, is similar, but the specifics differ because the model works differently.
Let's use the example of a legal document summarizer. That sounds challenging.
Definitely. Dense legal text, lots of jargon. It needs abstractive summarization rephrasing, not just pulling out sentences. Model choice, maybe T5 small or T5 base. They're built for text-to-text tasks. Dataset, BILSUM, from the Hub US congressional bills and human written summary.
Okay, what are the key differences in the steps compared to classification?
Right. Step 1, load data, BILSUM. Features are text, the bill, and summary, the target. Split train test. Step 2, load model and tokenizer. Critically, use AutoModel for sexy SQL-M and its corresponding auto tokenizer. These are designed for encoder-decoder models.
CQC specific versions. Got it.
Step 3, preprocessing is more complex. You need to tokenize both the input text, the bill, and the target text, the summary. The target summaries become the labels. Also, T5 models often expect a prefix on the input, like summarize, to tell it what task to do, so you add that before tokenizing the input text.
Right, tokenize input and output, add prefix.
Step 4, use the SICTC data collator. So data collator for SIC to SIC. This is really important.
Buy a different collator.
Because it needs to handle padding correctly for both the encoder inputs and the decoder labels. And critically, it automatically creates the decoder imputeds needed for teacher forcing during training by shifting the labels right. It also makes sure the loss function ignores padding in the labels.
Ah, okay. Handles the specific needs of training sequence-to-sequence models.
Exactly. Step 5, evaluation. For generative tasks, accuracy doesn't make sense. How do you evaluate a summary? The standard is ROUGE.
Rouge.
Yeah, recall-oriented understudy for gisting evaluation. It basically measures the overlap of n-grams, word sequences, between the model's generated summary and one or more human-written reference summaries. So your compute metrics function needs to decode the generated token IDs back to text, decode the label IDs, and then feed both to the ROUGE metric from the evaluate library.
More complex evaluation? Overlap-based.
Yep. Step 6, training. Use seek to seek training arguments and seek to seek trainer. These have arguments specific to generation, like predict with generate true, which tells the trainer to actually generate summaries during evaluation, not just compute loss. Also, FP16 true mixed precision is usually a good idea for speed. Step 7, push to hub, same as before. And a final crucial point on evaluation here. ROUGE is just a proxy. It's quantitative, but imperfect. For production generative models, you almost always need a human-in-the-loop evaluation component, too. Human judgment is still the gold standard for quality.
Right. Numbers aren't everything with generation. Need humanized, too. Okay, fantastic. We fine-tuned 2 models, but they're just sitting there. How do we get them into production? What's the deployment landscape look like?
Right, the crucial last mile. There's a spectrum, really, trading off control versus convenience. At one end, DIY max control. You containerize your model, maybe using Docker and a web framework like FastAPI for the inference endpoint. You build an inference script, write a Docker file. Pro tip: don't bundle the huge model weights in the image, download them on startup. Build it, test it, push it to a container registry, deploy it on Kubernetes or similar. Total control, integrates with existing infrastructure, but high MLOps overhead. You manage everything, scaling, monitoring, security.
Okay, that's the deep end. Is there a middle ground? A sweet spot?
I think for many, Hugging Face inference endpoints hit that sweet spot. It's a managed service, secure, scalable, production-ready, workflow's super simple. Pick your model from the hub, yours or someone else's. Configure the endpoint cloud provider, instance type, security level, public, protected, private. Click deploy or use the API. The service handles containerization, provisioning, security, scaling, even auto-scaling down to 0 to save costs. Much lower MLOps burden.
Sounds convenient. What about the big cloud providers? AWS, Google, Azure?
Yep, they're the third category. Cloud-native services. Think AWS SageMaker, Google Vertex AI, Azure Machine Learning. These are great if you're already heavily invested in one cloud ecosystem. They offer tight integrations with their other services, data stores, monitoring, IAM. You'll find things like SageMaker's Hugging Face DLCs, deep learning containers, Vertex AI's Model Garden, Azure ML's Model Catalog. They all now have streamlined ways to deploy models directly from the Hugging Face hub. It's actually part of a fascinating strategic dance. Hugging Face kind of dominates the model development and sharing space, so the cloud giants build easy deploy from hub features to keep the deployment workload and revenue in their ecosystems. Hugging Face's own endpoint service is their countermove.
Interesting dynamics. But with these easy cloud options, is there a downside, a double-edged sword perhaps?
There can be. That one-click deploy magic is fantastic for getting started quickly. But the abstraction layer can sometimes make troubleshooting harder when things go wrong. You might run into sort of opaque object types or platform behaviors that aren't perfectly documented. Debugging can be tricky if you don't understand the underlying principles. So knowing how it works, not just clicking the button, is still valuable for production robustness.
Good point. So summing up the options.
Okay. DIY. Max control, low ease, high MLOps overhead. Best for expert teams needing full integration. HF endpoints. Medium control, high ease, low MLOps overhead. Great for fast, scalable deployment without heavy infra work. Cloud native. High control within that cloud, high ease, medium MLOps overhead. Best if you're deep in one specific cloud platform.
Perfect summary. But deployment isn't the end, is it? Models don't just run perfectly forever. This brings us to LLMOps. What is it, and how is it different from regular MLOps?
Exactly. Deployment is just getting started. LLMOps is MLOps, specialized for the unique lifecycle of LLMs. Key differences. Traditional MLOps often focused on training models from scratch. LLMOps is heavily centered on transfer learning, fine-tuning existing giants. The cost profile shifts too. Less about massive upfront pre-training costs, more about continuous inference costs at scale. And there are new components in the lifecycle. Prompt engineering, versioning prompts, managing complex chains like RGET pipelines, incorporating human feedback loops. Plus, evaluation is way more complex. It's not just accuracy or F1, it's subjective quality. Coherence, relevance, avoiding hallucinations, bias. Much harder to measure automatically.
So a big part of LLMOps must be keeping the model performing well over time. How do you monitor that? Models drift, right?
They absolutely do. Performance degrades. Proactive monitoring is key to catching it early. Two main types of drift. Data drift, also called input drift. The kind of prompts coming in changes, maybe slang evolves, user needs shift, the input distribution changes. And model drift, or performance drift. The model's answers get worse even for similar inputs. Maybe the real world changed, making yesterday's right answer wrong today.
So how do you effectively monitor for both?
It needs a multi-layered approach. First, basic performance and cost metrics. Latency, throughput, error rates, token usage costs. Second, output quality monitoring. This is harder. You might use other models to check for toxicity or PII, statistical checks on output length or vocabulary, maybe sampling outputs for human review. You need ways to spot hallucinations, bias, relevance drops. Third, explicit drift detection. Convert inputs, prompts, and maybe outputs into embeddings. Then use statistical methods like KL divergence or population stability index, PSI, to measure if the distribution of these embeddings is changing significantly over time compared to the training or validation data. The goal isn't just monitoring, it's observability. Seeing that there's a problem isn't enough. You need to understand why. That requires good logging, tracing across your pipeline, tools for root cause analysis.
Okay, monitoring detects problems. How do you fix them efficiently? Retraining manually sounds slow.
Automation is key. That means CI/CD pipelines tailored for LLMs. Think automated workflows. When new labeled data arrives or monitoring flags drift, it triggers a pipeline. Maybe run some data validation tests, kicks off a fine-tuning job on the new data, automatically evaluates the new model against the old one on a holdout set. If the new model is better, the pipeline can automatically register it and even deploy it.
So automated retraining loops.
Exactly. Tools like Kubeflow pipelines, MLflow, Airflow can orchestrate these steps, pull data, fine-tune, evaluate, register. And for the deployment part of CI/CD, tools like Jenkins for CI, maybe Spinnaker or Argo CD for continuous delivery, using safe rollout strategies like blue-green deployments or canary releases.
Makes sense. Now, what about security? LLMs feel like they open up a whole new can of worms for attacks.
They absolutely do. New, complex attack surfaces. The OSP Top 10 for LLM applications is a great resource here. During fine-tuning, big risks include training data poisoning. An attacker sneaks malicious examples into your training data to create backdoors or biases. Mitigation, rigorous data validation, anomaly detection, securing your data pipelines and storage, regular testing for unexpected behaviors.
Poisoning the data. Scary. What else during tuning?
Sensitive information disclosure. The model memorizes sensitive stuff from the training data PII, secrets, API keys, and might spit it out later. Mitigation here is non-negotiable. Aggressive data sanitization before training, anonymization, pseudonymization, replacing secrets with placeholders, and supply chain vulnerabilities, using a compromised pre-trained base model or a vulnerable library or even a poisoned dataset from an untrusted source. Mitigation, use models and datasets from trusted sources like the hub, carefully vet dependencies, run training in secure, isolated environments.
Okay, those are tuning risks. What about when the model is deployed and serving users?
Top risk there is prompt injection. Malicious users craft prompts to bypass your instructions or safety filters, maybe tricking the model into revealing system prompts or executing unintended actions through tools you've given it access to. Mitigation is tough, an active research area, but includes strict input validation and sanitization, trying to clearly separate trusted instructions from untrusted user input, and applying least privilege if the LLM can call external tools or APIs.
Right, the prompt injection problem. Tricky.
And another big one, insecure output handling, just blindly trusting what the LLM says and passing it directly to backend systems or rendering it in a web UI. If the LLM output contains malicious code, like JavaScript for XSS or SQL commands because it was tricked by prompt injection, you've just enabled an attack. Mitigation. Treat LLM output as untrusted user input. Always validate it, sanitize it, and code it appropriately before using it in databases, APIs, or front end.
Never trust the output. Got it.
And maybe the most critical piece tying all of LLMOps together, especially for long-term improvement, is the feedback loop. Building the infrastructure to collect user feedback, explicit thumbs up down ratings, corrections, and implicit signals like whether they copy the answer or abandon the session, processing that feedback and using it to identify weaknesses and generate new data for retraining, that's absolutely vital. It's what separates a static prototype from a truly learning, improving AI product. Often the hardest part to get right.
That's a great point. The feedback loop closes the circle. Okay, we have covered an incredible amount of ground today. Really, the journey from just being a user of generic AI APIs to becoming a creator of these specialized production-grade models. It feels like a fundamental shift, like you said, from just using AI to actually building it as a unique, defensible capability.
Absolutely. We've seen that specialization is where the value lies now. We saw how PFT techniques, especially LoRa and the amazing QLoRA, have really democratized fine-tuning, made it practical. We explored the Hugging Face ecosystem, the hub, the libraries like Transformers and PEF, the trainer as this incredibly powerful standardized toolkit that just accelerates everything. And then bridging that gap to production requires smart deployment choices, balancing control and convenience. And finally, LLMOps provides the framework for monitoring, automating, securing, and continuously improving these models once they're live.
So wrapping up, what does this all mean for you, our listener, on your journey with AI? Mastering this whole end-to-end skill set from fine-tuning strategy and techniques through deployment to ongoing maintenance and security with LLMOs, that's really how you become a true model specialist. The demand for people who can safely and effectively build, specialize, deploy, and manage these powerful generative models. It's not just going to grow. It feels like it's becoming absolutely essential in shaping what comes next for intelligent applications. Makes you think, doesn't it? Where does your journey into specialized AI take you from here?